Welcome to AP Chemistry at Honeyniga High School. Today we're going to look at a couple of equilibrium problems. Now in the first problem we have a reaction between sulfuric chloride and it's decomposing to make sulfur dioxide and chlorine gas. Now one of the things it says in the problem, so when you read through you need to note a few things. One, it says the reaction is endothermic. Well, there's a reason they probably give you that. Two, they give us the mass of the SO2Cl2. So one of the things I know I'm going to need sooner or later is probably how many moles is that, because molarity deals with that, and if we're dealing with pressure we need to know moles and so on. So one of the things you really should do here is use the molar mass of the substance, which is 135.1 grams per mole, to calculate how many moles. So I'm just going to go ahead and do that up here because we're probably going to need that at one or multiple points throughout the problem. So that's how many moles we've got of that substance in the reaction. Now the other thing, since this is a gaseous system, and whenever you go to Kc, Kp, we need to know the change in number of moles, it's probably worthwhile to note that the delta N in this case is going to be 2 on the product side, 1 on the reactant side. We got a delta N of 1 in the reaction. May or may not be useful, but it's something that's worth noting. Also notice they give me the volume is 1 liter, which tells me that's the molarity of our reactant. And it also tells me the temperatures in Kelvin, which is what we need it in if we're doing KCKP stuff or PV1RT stuff, so that looks good. So those are the things you should notice at the beginning of the problem. Now, when you get into the question, it says, what would be the pressure in atmospheres in the bulb if no dissociation of SO2Cl2 occurred? In other words, what would be the pressure in here if all of this stayed as SO2Cl2? Well, we know we've got this number of moles of that substance, and it's asking about pressure. So pressure in moles, that sounds like PV equals nRT. And they give us a temperature, we've got the moles, they give us the volume, and so forth. So it sounds like a relatively straightforward calculation. The pressure would equal nRT over V. So at this point, you just have to plug in your numbers. The number of moles was 0.025973. The R value, notice or remember when we're dealing with R in this chapter, we use the atmosphere one, which is the 0.0821, and that's liter ATM per mole Kelvin. So right away I see moles here, moles there. They're probably going to cancel. And the temperature given was 375 K, and that's going to be divided by the volume, which in this case was given as 1 liter. So that simplifies things a little bit. So liters cancel, Kelvin cancels, mole cancels. We're going to be left with 0.800 ATMs to 3 sig figs. So that would be our answer to that first question. If it doesn't dissociate, all of it is going to contribute towards our pressure. Now, second question, when the system has come to equilibrium at 375, so now we're dealing with equilibrium. The total pressure in the volt is found to be 1.43 atmospheres. Calculate the partial pressure of all of the gases. Sounds to me like we should set up a icebox. So we're going to start with the reaction, and the given reaction was SO2Cl2, and that was in equilibrium with our two products, which would be SO2 and Cl2 gas. Now, when we set up our ice table, first thing we need to do is look at what was given in the problem. Well, if you take a look, they don't really give us much of anything, but they do tell us that the total pressure is 375, or I should say the temperature is 375 the system, and they give us that the total pressure was 1.43 atmospheres. That's going to become useful in a second. So if you go back to the previous problem, we just calculated that this was our pressure if we had all of that substance. And we're going to let this reach equilibrium, which means there's none of either of these. This is going to be going down by some amount by the stoichiometry. That's going to be going up by that exact same amount. And therefore, from an equilibrium standpoint, the equilibrium pressure of our SOCl2 would be 0.800 minus x, and these would each be x. Now at this point it sounds suspiciously like we're going to calculate the Kc and write the expression. We're going to have all those x's and maybe have the quadratic, except for the fact that they tell us this. They said the total pressure is 1.43 atmospheres. So what that means is these three that I have here in my ice table, well, those need to add up to that total pressure. So we've got a very simple way to determine X here. So when we add and subtract, we figure out that X in this particular problem is going to equal 0.63 ATMs. So if we do some algebra, we find out that X is 0.63 ATMs. Now, going back to our ice table, that would then equal our concentration of, or in this case pressure, the pressure of the SO2 and the pressure of the Cl2. Those both equaled X. So now we've established what those two partial pressures are. We're 2/3 of the way done in the problem. All we really need to do is take 0.800 and subtract X in order to determine what the pressure of our remaining substance is. So that would actually give us what the SCl2 pressure was. So what will be left here is going to end up being 0.17. Oops. Let me write that correctly. 0.17 ATMs. So that would answer part B. Those are our three partial pressures at equilibrium. Moving on to part C, it says, find the Kp for the decomposition of SO2-Cl2 at 375 and calculate the value of the equilibrium constant you have given and specify its units. So what we really need to do here is take a look at what we knew from the last problem. Remember in that last problem, we just determined that the equilibrium pressures of our two products were 0.63 and our reactant was 0.7. So if we set up our K expression here, now based on the equation, Kp would equal SO2 pressure times Cl2 pressure over the SO2-Cl2 pressure. And we knew from the previous problem that both of those were 0.63 and the pressure on the bottom was 0.17. So Kp in this particular problem would equal 2.3. Remember, K values don't have a unit. So that would be our calculation of Kp. Now, next thing it does is ask us to turn around and find Kc. Now remember, our equation was the Kp was going to equal the Kc times RT raised to the power of the change in N. And remember, we calculated that this was 1, and we just found out that this was 2.3. So that gives us a quick route to solve for Kc. So Kc is going to equal, mathematically, our 2.3 divided by RT. And when we plug in our numbers, remember R is going to equal 0.0821, our atmosphere value. And the temperature conveniently was given in the problem in Kelvin, so that's 375. When we plug in our numbers to two significant digits, we end up with 0.076 as our Kc. Last and final one for problem 1 was to answer the question, if the temperature were raised to 500 K, what effect would this have on the equilibrium constant? Explain briefly. Well, on the surface, one thing some people mistakenly do is they'll look at this one and they, oh, temperature's on the bottom, and if our temperature goes from 300 to 500, and that's on the bottom, it was getting bigger, that would make this get smaller. The problem with that is you have to understand, if you change the temperature, you're changing the K value. So we can't just look at that equation. We have to think about what was given in the problem. Now, it said the reaction was endothermic. And since the reaction is endothermic, that would mean that increasing the temperature of the system would favor the production of products. Why isn't this thing? That's why. We want that thing to fade in. So what I was just saying here, looks like I have to keep it there. Looks like it's not going to give it to us, so I guess I'll just have to write it. Since the forward reaction was endothermic, so remember, forward was endothermic. Increasing the temperature would favor the production of the products. So if we've got energy on this side of an equation and we're increasing the energy, that's going to shift equilibrium to the right, and it's going to cause our product concentrations to go up. Now, if we're increasing our products, that is going to increase because our K is products over reactants. If this is going up and that's going down, our K value should increase. So the reasoning here to answer the final question in part one is if it's an endothermic reaction, adding energy, so increasing the temperature, would shift equilibrium to the right, which would favor the production of products, making the K increase. So the equilibrium constant would increase in this case. Now, next problem, problem number 2. At an elevated temperature, SbCl5 decomposes into SbCl3 and Cl2 gas by the following equation. So once they're giving us this reaction, notice I've got a gas system again, so one thing I can take a look at here is our delta N. That's going to equal 2 minus 1. So the delta N here is also 1. When I get into A, notice it gives me mass, so I can change those to moles. And another thing I want to fix right here at the beginning, notice it gives the temperature in degrees Celsius. Well, all the math we end up doing has the temperature in Kelvin. So that means this has to be a 455 K. So when we go to solve this problem, those will be useful ideas throughout the course. Now, first thing it says is 89.7 grams. And I already mentioned that whenever we're given a mass, it's useful to get to moles. So that's what I'm going to start off with. I've got this many grams of SbCl5, and they have conveniently given me the molar mass here. So thank you for that. So 299.0 grams is 1 mole. So doing my calculation in the calculator, I would end up with the number of moles equaling 0.300 moles to 3 sig figs. Now, since molarity is number of moles divided by the volume, and it says the volume is 15 liters, all I have to do is divide that by 15, and I calculate my molarity. So in this particular problem, I've got 0.0200 molar. So what's the concentration in moles per liter? Well, it's just moles divided by liters, and that's what it would be before any decomposition happens. That sounds suspiciously like something I would use in an ice box for an initial value. So next question, what is the pressure in atmospheres of SbCl2 in the container before it decomposes? Well, notice it's talking about pre-decomposition again. So I'm not jumping into an ice problem yet, but I do have something right here that's going to help me answer this. So when I'm dealing with pressure, that would be PV equals nRT for the problem. And if it's asking what the pressure is, just like we did in the previous problem, that would be nRT over V. So when we plug in our numbers, we've got 0.300 moles that we calculated. We've got our R value, which remember in this chapter we're using the atmosphere value, so that's liter ATMs over mole Kelvin. And our temperature given the problem, well, it wasn't given in this, but we already figured out that that would be 455 Kelvin, and the total volume of this container was 15.0 liters. So at this point I can plug and chug, and I can calculate the pressure to 3 sig figs is 0.747 ATMs. So now I know what my molarity is at the beginning, and I know what my pressure is. So no matter which way I go, a KC or a KP problem, I've got my molarity and my atmospheres of pressure to handle that. So notice right away in the next problem it says, if the SbCl5 is 29.2% decomposed, so now the reaction has progressed, and when I reach equilibrium, 29.2% of my substance has decomposed. Calculate the value for Kc. So this sounds like I'm going to be doing an ice table. So I'm going to start with my reaction. SbCl5 is in equilibrium with SbCl3 and Cl2. Now, I knew what my amount was at the beginning, so I know initial conditions here. Now remember from a second ago, I just calculated that the molarity at the beginning was 0.02 molar. So if I set up my ice table here, I know my initial molarity is 0.022 molar. Now, pre-decomposition, I would have 0 of each of these, and then it decomposes. So this is going to go down, and these are going to go up by x. So I know I've got 0.0200 minus x plus x, and plus x. So I'm just going to call those values x there to simplify. So that would be my setup in this problem. Now, how do I go about calculating what it wants, which is our Kc? Well, to get to Kc, I need my equilibrium concentrations. And right now, I've got x's in those spots. So how can I get rid of my x? Well, the key right there is what it said, 29.2% of it decomposed. So if I take 29.2% of my original concentration here, which my original amount of moles was 0.300, or my original concentration was 0.02, I can take 29.2% of that and I can calculate exactly what this x is. So if 29% of it, 29.2% of it decomposes, what is 29.2% of that? Well, it turns out that that is 0.00584 molar. So 29% of it decomposes, and that was my original. That means that's how much is going to drop. So this is going to equal, for this problem, what my x value is. So at that point, I can plug that in for each of these, do the math here with that x and calculate that, and I can figure out what my Kc is. So I'm going to get SbCl3 on top, and we'll deal with concentration. So I'm going to do brackets here, and Cl2. And on the bottom, we have to have our SbCl5. Now, all we need are our concentrations, which on the top, remember that was given a second ago as 0.00584 molar, and that was both of them. So we're going to square that, and that's going to be divided by 0.00584 subtracted from 0.02, and that gives us 0.0142 once we do the subtraction. So remember this. It's going to go right down there after we do the math. And then when I plug in, I end up with 2.41 times 10 to the negative third as my Kc. So that is what Kc is. Now, if I wanted to, I could use the Kp to Kc reaction to calculate Kp at this point. Okay, in our last problem here, part C, it says, in order to produce some SbCl5, a 1.00 moles sample of SbCl3 is first placed in an empty 2-liter container, maintained at a temperature different from 182. So we know that our K is going to be different than what it was before. And it's telling us at this temperature, K equals 0.117. Now, how many moles of Cl2 must be added to this container to reduce the number of moles of SbCl3 to 0.700 moles at equilibrium? Okay, so here's our equation. Let's set up our icebox table. Now, it says at the beginning here that we have a 1 mole sample in a 2-liter container. So we know our initial concentration of SbCl3 here will be 0.500 molar. So that's what we've got at the beginning. So that's placed in the empty 2-liter container. That's its concentration. Now, it says how many moles of Cl2 must be added to this container to reduce the number of moles of SbCl3 to 0.700. So we don't really know how much of that must be added as well. So in order to get a reaction, we have to add some SbCl3 and some Cl2. But the question really is, how much Cl2 do we have to add along with the 0.500 molar SbCl3 in order to end up with a final number of moles of SbCl3 of 0.700 in 2 liters. So remember, since that's in 0.700 moles in 2 liters, we know that this has to end up, when all is said and done, when we reach our equilibrium, as 0.35 molar. So we know in our icebox situation here, we know that initially we don't have any of this, and we're adding these two things together, SbCl3 and Cl2. And we know exactly how much SbCl3 we had in there, but we don't know how much Cl2 we had. But we do know we want to end up with at equilibrium. So this is in our E spot, 0.350 molar SbCl3. Well, we know that this is going to go down in our reaction. And we know by the stoichiometry, this is going to be going down by the exact same amount because it's a 1-to-1 stoichiometry. So we don't really know how much Cl2 we had in there to start with. That's actually what they're asking us to find. But they do tell us the equilibrium concentration of SbCl3. But what we really need to know is what that concentration is. Because if we can find this concentration and we know what X is, we can find out how much Cl2 we started out with initially. So we know our initial conditions. We have 0 of SbCl5, and we know we had 0.500 molar SbL3. We just don't know how much chlorine was in there with it. And we know as the reaction proceeds to equilibrium that SbCl3 is going to go down by X, the Cl2 will go down by X, and therefore the SbCl5 will go up by X. Now, they also tell us in this problem, actually, so that's got to be X. And what we know in this problem is that where is it at? Right there. The Kc expression, which would be the Kc is going to equal the concentration of SbCl3 over the concentration of Cl2, or times the concentration of Cl2, all over the concentration of SbCl5. And we know that this actually equals 0.117. Now, if we take a look at what we've got at equilibrium here, we know that we started with 0.5 molar. That's what we started with here. And we know we're going to end up with that. So we can solve for X. So based on this equation, X is not an unknown. X has to be the difference between these two values. So X has to equal 0.150. So we know that X is going to equal 0.500 minus 0.350. And that means X is going to equal 0.150. So I know not only that this is 0.350 for SbCl3 at equilibrium, but I also know that this is going to be 0.15 molar. So we know what X equals here. Now, I still don't know what Cl2 is because I don't know what I started with here. But if you take a look, we don't know what this value is, but I now have the amount of SbCl5. So let me clear this out of the way here. So we know that 0.117 is going to equal SbCl5, which was our SbCl3, which is 0.350 molar, times our Cl2, which is really what we're trying to find here, over SbCl5, which we just figured out was 0.150 molar. So solve for Cl2. So we know Cl2 is going to equal 0.17 or 0.117 times 0.15 divided by 0.30, and we can calculate the Cl2 here has to equal 0.0501 molar. So now I know what that is. I know that is 0.0501 molar. And remember, we figured out X was negative 0.150 here. It's going down by that much. So how much did we have initially? So 0.0501 minus our 0.150 tells us we started with 0.200 molar Cl2. So this had to have begun with 0.200 molar. Now look at what the question is. It says how many moles of Cl2? Remember, it was 0.200 molar in 2 liters. Well, 0.200 molar. That is that many moles for every 1 liter. And if I multiply that by my 2 liters, I have 0.400 moles. That's what I had to have at the beginning. So because they gave us the I and the E for SbCl3, we could find X. Once we knew what X was, we could find out what the equilibrium concentration of SbCl5 was. And from there, we could use that to calculate this value. And since we knew the X was this, we could use that to calculate that. And once we knew that, we could use that and the 2 liter volume to calculate how many moles we started off with. So the final answer to this one is 0.400 moles. And that ends our equilibrium practice.